Lesson 7-4, Solving Compound Inequalities. In this lesson, you learn to solve problems by making a diagram, to solve compound inequalities and graph their solution sets, and to solve problems that involve compound inequalities. Why is it important? Because you can use inequalities to solve problems involving chemistry and in physics. And let's take a look at an example in chemistry. The largest fish that spends its whole life in fresh water is the rare plabok found in Mekong River in China, Laos, Cambodia, and Thailand. The largest specimen was reportedly 9 feet 10 and 1/4 inches long and weighed 533.5 pounds. Such rare fish are sometimes displayed in aquariums. Aquariums can house freshwater or marine life and must be closely monitored to maintain the correct temperature or pH for the animals to survive. Okay, pH is a measure of acidity. To measure the pH, a scale with values of 0 to 14 is used. Okay, one such scale is used in the diagram below. And this is a good example of a pH scale. Okay, where you have 7 as the neutral number, and as you go to the left of 7 going to 0, less than 7 will give you increasing acidity. As you go to the right of 7, okay, from 7 to 14, that'll give you decreasing acidity. Okay, a good example of some substances. Okay, water, okay, has a pH scale of 7. That means it is neutral. Blood has a pH scale of 7.2, shampoo 5.8, and so on and so forth. And if you look at the the pH scale, stomach acid has 1. Okay, the pH scale of stomach acid is 1. That means it's very acidic. Okay, because this is where you digest your food, and the acids are used to digest foods. Lemons is 2.5, vinegar 3.0, and you look at to the right, lye is 13.8, ammonia 11.5, milk of magnesia, soap, and so on and so forth. Okay, and to the left of the pH scale below 7, you call them acids, and to the right of the pH scale, you call them bases. Okay, we're going to talk about pH scales later on in science. So if we let P represent the value of the pH scale, we can express the different pH levels by using inequalities. For example, an acid solution will have a pH level of P is greater than or equal to 0 and P is less than 7. So when considered together, these two inequalities form what we call a compound inequality. This compound inequality can also be written without using and in two ways. Okay? So these are possible ways of writing your compound inequality. Okay? So this means that P is greater than or equal to 0 and less than 7. Or P is less than 7 and greater than or equal to 0. Okay? So the statement 0 less than or equal to P, P is greater than or equal to 0 and less than 7 can be read as, well, I just did it. 0 is less than or equal to P, which is less than 7. So the statement 7 greater than P greater than or equal to 0 can be read as 7 is greater than P, which is greater than or equal to 0. Okay? So the pH levels of bases could be written as follows, just like acids. P is greater than 7, P is less than or equal to 14, or 7 is less than P, which is less than 14. 14 is greater than P and greater than 7. Okay? So we will graph this inequality later on in example or in exercise 6. That's going to be one of your classwork exercises. Okay? Oops. You can draw a diagram to help solve many problems. Sometimes a picture will help you decide how to work on a problem. Okay? Other times the picture will show you the answer to the problem. On May 6, 1994, President François Mitterrand of France and Queen Elizabeth II of England officially opened the Channel Tunnel connecting England and France. Okay. After the ceremonies, a group of 36 English and French government officials had a dinner at a restaurant in Calais, France, to celebrate the occasion. Suppose the restaurant staff used small tables that seat 4 people, okay, placed end to end to form one long table. How many tables were needed to seat everyone? So, in this case, uh, drawing a diagram would be a big help. Okay, so first we need to create our table. Let me find my table. Oh, it's probably down here, right here. Okay, so these are the number of people. The table is right here. So if this is the table that you draw, it says how many tables were needed to seat everyone. Okay, and if you look at it very carefully, if you put this table next to each other, there'll be one person on each side and one person on the other side of the table and one at both ends, okay, of the table. Okay, so drawing would be helpful in this type of problem. And if you notice here, 10 tables will seat 22 people. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and there are 22 people. If we use an extra table, we can seat 2 more people. Now let's look for a pattern. If 10 tables can sit 22 people, okay, if we add another table, it can sit 24 if we add it in the middle. If we add one more table, it's get 26. One more table, 28. 14 tables, 30. 15 tables, 32. 16 tables, 34. And 17 tables, 36. Okay? So if you look closely, okay, this pattern shows that the restaurant needed 17 tables to seat all 36 officials. So here, right here. So you can see by drawing a diagram how you can solve a particular problem. Okay? So a compound inequality containing and is true only if both inequalities are true. So when you see the word and, okay, in a compound inequality, it is only true when both inequalities are true. Okay, that's the graphs of a compound inequality containing and is the intersection of the two inequalities. Okay, the intersection can be found by graphing the two inequalities, then determining whether these graphs overlap. In other words, draw a diagram to solve the inequality. Okay, so before we go to example number 2, let's talk about intersection. Before that, let's read this. The logic symbol for and is an upside down V. You can write x is greater than 7 and x is less than 10 as x is greater than 7. Okay, is the intersection. Okay, and x is less than 10. So the upside down V is symbol for and, okay, or intersection. When you take your entrance exam, for example, intersection can be also an upside down U. Okay, so let me give you an example of what intersection is. Let's say you have set A. Okay, make that black. Let's say set A. Let me erase this intersection sign. Let's say set A is a group of numbers 1, 2, and 3. And set B is a group of numbers it stopped. Let me turn this back on. There you go. Set B is a group of numbers 3, 4, and 5. So this is set A. Put them in this set right here. And set B 3, 4, 5. So if I say what is the intersection of A and B, so the upside down U is also an indication of intersection. That simply means that if I have these two sets, okay, and I make these two circles right here, right there. And let's say this is set A. I'm going to make it small. And this is set B. If I say intersection, what it's saying is what is common to both sets. Okay, so I would put the I would put the 1 and 2 here, 4 and 5 inside this circle, and 3 in the middle. So the intersection of A and B would be 3 because 3 is common to both sets. So when you see the word intersection, it's just saying what is common to both sets. So in this case, when you say the graphs of a compound inequality containing end is the intersection of the graphs of the two inequalities, what it's saying is what is common, okay, between those two inequalities. Okay, and in this case, instead of Venn diagrams, we are going to use, okay, line graphs to show the intersection. So let's, without further ado, let's go on to example number 2. Graph the solution set of x is greater than or equal to -2 and x is less than 5. Okay, so first, let us graph x is greater than or equal to -2. Okay, and since it's greater than or equal to, it's a closed dot, and pointing away from the variable goes to the right. Okay, and let's graph x is less than 5. Okay, x is less than 5 would be an open dot on 5, and since it points to the variable, it goes to the left. Okay, so from there, let me just free up memory because it's slowing down a little bit. Yep, it is slowing down. Okay. All right. So it's an open dot on 5 going to the left, and if you notice, there is a pink line on -2 and 5 because that'll tell you, we'll know what that is later on. And if we get the intersection of those two, okay, which means what is common to both graphs. So this graph goes this way, this graph goes this way, and what is common to both graphs is this line right there in the middle. Okay, so we get that closed dot, we bring it down there, right there. That closed dot is brought down there, and that open dot is brought down. But if you notice, we're only getting what is common, which is this line right here, and that's what that was what was brought down. So the intersection of x is greater than or equal to -2 and x less than 5 is this graph right here. Okay, the solution set shown in the bottom graph is x such that -2 is less than or equal to 5 is less than or equal to x, which is less than 5. Note that the graph of x is greater than or equal to -2 include the points -2, and the graph less than 5 does not include the value of 5. So we basically just brought down the closed dot, and we brought down the open dot, and copy the line in between. Okay, so that is the intersection of the graph. X is greater than or equal to -2 and x is less than 2. And take note of this, the word and will always represent intersection. Okay? Let's take a look at example number 3. Solve -1 less than x plus 3, which is less than 5, then graph the solution set. Or we can also read this as solve x plus 3 is greater than -1 and less than 5. So if you notice, I read it as and, which means it's looking for the intersection of those two inequalities. Okay, so let's first express -1 or x plus 3 greater than -1 and less than 5 using the word and. I just said that. So it's going to be negative 1 less than x plus 3 and, okay, x plus 3 less than 5. Okay, so we simply solve for each inequality. So we subtract 3 to both sides, and we end up with x is greater than negative 4 or negative 4 less than x. On the other side, we subtract 3 to both sides, and then we have x is less than 2. Okay, now we graph each solution and find the intersection of the solutions. Again, when you talk about end, we're looking for the intersection between those two graphs, which means what is common to both graphs. Okay, so if we do that, okay, graphing the first one, negative x less than 4 will give you an open dot on negative 4. Since it's pointing away from the variable, the arrow goes to the right. Okay, and graphing x is less than 2, you have an open dot on 2, and since it's pointing to the variable, the line points to the left. Now if you notice, the pink line indicates the boundaries between the two, negative 4 and 2, and you simply bring down that open dot to the third graph, and that open dot to the third graph as well, and simply write the line in between. Okay, so the intersection of these two graphs would be x is greater than negative 4 and less than 2. That would be that intersection right there. Okay, so the solution set is x such that x is greater than negative 4 and less than 2. Okay, let's take a look at the next example. Example number 4. The following example shows how you can solve a problem by using geometry, a diagram, and its compound inequality. Maya and Luis hope someday to compete in the Olympics in pairs in ice skating. Each day they travel from their homes to an ice rink to practice before going to school. Luis lives 17 miles from the rink and Maya lives 20 miles from it. If this were all the information you were given, determine how far apart Maya and Luis live. Okay, so we have information that we need to find out, and that's how far apart they live, but they didn't tell us in what direction they live in. So let's do this. Maya lives 20 miles from the rink and Luis lives 17 miles from the rink. We do not know the relative position of Maya's and Luis' homes in relation to the rink. Our plan is to draw a diagram of the situations. So let S be the location of the skating rink. Okay. Since Luis lives 17 miles from the rink, we can draw a circle with a radius of 17. Luis will live somewhere on that circle. Likewise, we can draw another circle with a radius of 20 for the location of Maya's home. Okay, so these are the circles we can draw. That would be Luis's location, 17 miles radius around the rink. And if we draw another circle around it, the blue circle would represent Maya's location, okay, somewhere around the rink. So her location would be one of the points in the blue circle, and Luis's home location would be one of the points in the red circle. Okay, so from there, after drawing it out, okay, we go to trying to solve our problem, and we examine 3 possibilities for the location of Maya's and Luis's home. And let's look at these 3 possibilities. First, Maya and Luis live along the same radius from the skating rink. Okay, that's the first possibility. Another possibility that we can gather is that Maya and Luis live in opposite radii from the skating rink. And the last possibility, Maya and Luis live somewhere other than locations described in 1 and 2. Okay, so let's define our variable. Let L and M represent where Luis and Maya live respectively. And let's examine the first situation. They live along the same radius. So that means if they're in the same radius, this is how it would look like. So this would be Luis's home, that would be Maya's home. 17 miles and 20 miles. And on the second situation, they live on opposite radii. That means if Luis lives here, Mai would live on the opposite side, okay, on the other side. And in the third situation, it does that means that they are in locations other than the one described in 1 and 2. So you can probably do this. Okay, Luis lives here, Mai lives there. Okay, that's the third situation. Second situation, opposite radii. Third situation, somewhere other than 1 or 2. So if you take the first situation, the distance is 3 miles. They live 3 miles away from each other if they live in the same radii. If they live in opposite radii, they are 37 miles apart. And finally, in the third one, by the triangle inequality theorem, okay, the distance must be less than 37 miles and greater than 3 miles. Does that make sense? So it should be less than 37 miles because of this one. Okay, the maximum distance between them would be 37 miles, and the least distance between them would be 3 miles. Okay, so if we follow that same logic, okay, you don't even have to look at the triangle inequality theorem, but if you follow the same logic, okay, the maximum distance they would have from each other would be 37 miles, and the minimum distance they would have from each other, some would be 3 miles. Okay, so the distance d can be described by the inequality. D is greater than or equal to 3 miles and less than or equal to 37 miles. And that's how drawing a diagram can help us solve this type of a problem. Okay, so diagrams 1 and 2 show the least and greatest possibilities. We're now checking our answer. To convince yourself that the statement with the diagram 3 is always true, you may want to sketch a different triangle. Okay, so that's one way of checking it. Okay, so this is now a possible inequality. We can pose, okay, the distances between Mai's and Luis's homes. Okay, and before we go to example number 5, the secret word for this lesson would be Broncos. Again, secret word would be Broncos. Move on to example number 5. Another type of compound inequality contains the word or instead of and. A compound inequality containing or is true if only one or more inequalities is true. Okay, remember in the word and means that both inequalities should be true for the compound inequality to be true. In the word or, okay, you only need one inequality to be true, okay, for the entire inequality to be considered true. So the graph of the compound inequality containing or is a union of the graphs of the two inequalities. Remember, intersection is an upside down U. The symbol for union is actually a U. So going back to my original example, if I have set A, okay, being 1, 2, 3, and set B being 3, 4, 5, if you are asked for the union of A and B, it would be the set of 1, 2, 3, 4, 5. So that basically includes all the elements of both sets. Okay, so in this case, okay, that is one of the if you encounter this probably in your entrance exam, the U would represent union, the upside down U would represent intersection. Okay, again, you can also use a Venn diagram to illustrate this. Okay, so let's take a look at this one, see how this works in a union. We're asked to graph the solution set of x is greater than or equal to -1 or x is less than -4. Okay, so let's graph the first one. X is greater than or equal to -1. Okay, since it's pointing away from the variable, it's a closed dot on -1 and going to the right. X is less than 4 will be an open dot, okay, on -4, going to the left since it's pointing to the variable, and since it's a union and not an intersection, the word or represents union, we simply plot the two graphs. Okay, So you simply bring down that graph, x is greater than or equal to -1, and you simply plot x is less than -4, okay? And that would be the graph, okay? The last graph represents or shows the solution set, okay? Such that x is greater than or equal to -1, or x is less than -4. So one inequality should only be true for both inequalities to be considered true. Okay? So look at the difference between union and intersection. Let's take a look at the last example. Example number 6. Solve 3w plus 8 less than 2 or w plus 12 greater than 2 minus w and graph the solution set. Since it's the word or, okay, that means we are trying to find the union of the two graphs. Okay, so 3w plus 8 is less than 2, and we solve for w. That means we subtract both sides by 8, and then we have 3w less than -6. We divide both sides by 3. We end up with w is less than -2. And on the flip side, we have w plus 12 greater than w plus 12 greater than 2 minus w, and we want to undo one of the w's because we have variables on both sides of the inequality. So we add w to both sides. You end up with 2w plus 12 greater than 2. Undo positive 12 by subtracting 12 to both sides and divide both sides by 2. End up with w is greater than -5. So if we graph the solution and find the union of the two, okay, union is simply putting them together. We have w less than -2 is an open dot on -2 going to the left, and w greater than -5 is an open dot, okay, going to the right. Now look closely, okay. If we put them together and we put these two graphs on top of each other, what would be the solution set? Okay, if we merge those two graphs, you'll have a line that looks something like this. Okay, so if you graph these two lines, okay, you'll have a straight line all across your number line. So the last graph shows the solution set. Solution set, since the line is on the number line, you have x such that x is a real number. So any value of x will make this inequality true. Okay, so if you superimpose this graph and put it on top, or put the upper graph and put it in the second graph, you will notice that they will overlap each other and you will have a whole line. All right? Try some odd numbers if you are having difficulty understanding this, and go back to the video and look at the answers at the back of the book. Again, you watch for understanding, okay, not just to turn in the summary. Thank you for watching.